Hello, guys, welcome back. A very good morning to you. And we are here today with an interesting generalization of a simple problem, which is from ISI 2017 PSA. The problem asks you the following, that if you have a square, okay, if you have a square, let's say ABCD with side lengths, not side lengths, but with the name of the vertices ABCD, then what are the ways to color this with three colors? Let's say you have red, blue, and green. What are the ways to color this? The vertices A, B, C, D says that the no two consecutive the adjacent vertices have the same color, right? So the problem is not very hard. The problem revolves on this following fact, that let's take you have two cases out here. Case one is that B and D have same colors. Let's write B is equal to D, to be very specific. And B is not equal to D. If B is equal to D, we have what? Let's first select A. For A choice, the choice of A, we have three possibilities, right? Three possibilities. Now comes the choice of B. Now there are two cases. If B and D are equal and if B and D are not equal. So this is important. This is the tree diagram. This tree diagram really helps you to understand what's really happening. B is equal to D and B is not equal to D. And if B is equal to D, you have two options for both. Because if B is equal to blue, if D is equal to blue, if B is equal to green, blue is equal to D is equal to green. So it's like, yes, so two options, and B and D are not connected. But if B is not equal to D, there are only also two options. Two options for B and only one option left for D. Only one option left for D. So two options again. And therefore, what about the C aspect? Now, given this scenario, what about the C aspect? C has, if B is equal to D, understand, if B is equal to D, C has again two options, because it increases the option of A. If A was red, B and let's say both are blue, then C has now option of red, but not blue and green. So two options again for C. And if B is not equal to D, these two are distinct, C has only one option. Why? Because if the two are distinct, only one option, that was the possibility of A. So therefore, total we have in this partition, we have 3 into 2 into 2, that is 12. And in this partition, we have 6. So total 18 options. The next question is that, can we generalize this? So one of my students asked me, can we generalize this problem to the case where there is a cycle or it's an n-gon? How we can color this with the same method, with the same algorithm, with R colors, such that no two adjacent vertices have the same color. Like generalize the problem to n gone and r colors instead of 4 gone and 3 colors. This is the question we're gonna address now. Let's move on to the question. So we will use the same idea over here. Idea is a bit not the same idea, but it will be a, if you continue in this manner, it will be really hard. Okay, it will be really hard because you don't know, you have B and D over here, but there it will be B and D, and then take the before pair also, like the what will be before that. So this method is a bit harder, but we can try to capture this core idea. The core idea is that, let's say, this is a n plus 1th vertex of a n plus 1th gone. Now it can happen that there's two vertices connected over here are distinct colors. Distinct. These two are distinct colors. Okay. Let's name it. Let's say P and Q. P is not equal to Q. And if P and Q is here, P is equal to Q. Now, if P is not equal to Q, it's equivalent to the fact that the rest of the cycle, whatever we have, if these two are distinct, that means if you consider this cycle, if you consider a cycle formed by these vertices, except the n plus 1th vertex, understand this. If you consider a cycle formed by these vertices, except the n plus 1th vertex, also the type 1 cycle. So let's define like type n cycle. That means let's define Pn to be the number of ways to color the nth cycle. This color a way of recurrence relation. So we get that in this case, understand this very carefully, in this case, P and Q are distinct colors. That means you can form the total number of ways to color this is same as coloring the cycle except this n plus 1. So let me show it to you. It's coloring cycle without this. That means with this except the n plus 1th vertex. So therefore, what do we get? We get that in this case, if P is not equal to Q, then we have Pn, because we are coloring the number of ways including the PQ except the n plus 1 times. Now observe that P and Q has one color because it's has two colors, okay, on their palette. On the vertex are different colors. So for the n plus 1th vertex, the possibilities are r minus 2 colors. So understand this very carefully. When P is not equal to Q, then essentially its term boils down that you can color the rest of the vertices except the n plus 1 in Pn ways. Why? Because it's exactly P is not equal to Q, so you can actually form a cycle here. And this means that it's a cycle which can be colored in R with R colors. Okay, that means the number of ways to color like till PQ is Pn. But since P and Q are different now, right? The n plus 1th vertex can be colored in r minus 2 ways because 2 are gone here. These two are gone. The two possibilities are gone out of the R colors. So R minus two ways. So this is for the n plus 1th vertex. This is for the rest of the vertex. And the second possibility is P is equal to Q. If P is equal to Q, the idea is to make it into something, like Pn minus 1, Pn minus 2. So what you do is that you take the previous one, R, let's say. Now, since P is equal to Q and Q is not equal to R, PR must be distinct, right? PR must be distinct. Q is not equal to R, right? Because they're adjacent. So therefore, whatever you have here, whatever cycle you have, can color therefore similarly this cycle. Okay, let me just take a better one. You can color this cycle. Since P is not equal to R, you can actually draw a line in between just like this. You can color this cycle length. It's of n minus 1 length. And P and Q are same. So essentially, it's this one ke liye, you can color this n minus, so n plus 1, so n minus n here, and n minus 1 here. So it's Pn minus 1 actually. The number of ways to color this is Pn minus 1 because all distinct colors, like not all distinct colors, but it's actually same as coloring P and R are distinct, and hence they're in kind of sense adjacent, and hence it's same as coloring the n minus 1 vertices over here. And P and Q together can be colored as, sorry, Q can be colored as the same as P, so it's fixed for Q. And this failure, you have only one color for P and Q together, so it's R minus 1 possibilities because one color is vested, right? This ke liye n minus 2 and this ke liye it's Pn. So you have two options. So Pn minus 2 has two options. Pn minus 2 has two options. Pn plus 1, sorry. Pn plus 1 has two options. These are the two options. So we have what? We have Pn plus 1 is nothing but Pn times R minus 2 for this first case where P is not equal to Q, plus Pn minus 1 times R minus 1 for P is equal to Q case. It's pretty interesting, right? And you can actually solve this in an easier way. That's your homework, the sequence problem. But one of the hint is the following, that you add Pn plus 1, Pn plus 1 plus Pn. So you get on the right hand side R minus 1 times Pn plus Pn minus 1. So if you define this to be some Qn plus 1, this turns out to be Qn. So you get Qn plus 1 is nothing but R minus some constant times Q, and this you can see it's geometric, right? You will say this is geometric. So you will get that Qn plus 1 is some R minus 1, some geometric, c to the power n plus 1 or something like that. Some constant sign c to the n. And it's Pn plus 1 times Pn. And then you can actually solve those set of equations to get Qn. It will be, I think it will be a AGP series or something like that. But essentially it's very solvable. So I will not tell you the method to solve this. It's your homework. Write down it in the comments how you solved it. But yeah, it's a beautiful problem. The idea of reconciliation, partitioning the whole thing and then counting it individually, it's really beautiful. I hope you enjoyed it, guys. Solve this question below, solve the sequential form below. Let us know in the comments. All the best. And yep, if you have tried, if you can try to color some other type of, not pictures like such structures, these structures are called graphs, then do let us know in the comments. All the best, and I will see you in the next video. Stay tuned and stay blessed. Bye bye.